Good morning. Today's topic is on gas turbine formula calculation. So those things we are moving. So you have in previous lecture you have seen the basic fundamental understanding of gas turbine. So it is having one compressor system, it is having one shaft, you have one combustion chamber, you have one turbine. So compressor compressing air, sending to combustion chamber or combustor, then you are harnessing energy in turbine. Now how to calculate the power, how much power you are getting in different so you have to go for TS diagram and PV diagram, and we have to see how to calculate efficiency and performance. So similar way we have calculated for IC engine. IC engine means reciprocating IC engine. This is also IC engine, but this is continuous flow IC engine. But reciprocating IC engine means like Otto cycle, diesel cycle you have calculated. So similar way we will see how to calculate for gas turbine system also. Okay, so gas turbine system already you have seen, while compressor is there, one turbine is there, fluid entry, combustion happening, exit is happening. Okay, so normally it will be open cycle, but sometime we draw as a closed cycle also. So 1 2 3 4. Okay, so compressor, turbine, combustion chamber or combustor. Okay, now TS diagram. So TS diagram it will be looking like this. So in Rankine cycle actually, you can remember Rankine cycle, TS diagram we have drawn like this. Okay, so this is Rankine cycle, but here my figure will not have any that vapor envelope because we are not condensing anything. Okay, so we'll have compressor 2 to 3 peak temperature or highest temperature will be at 3 actually after combustion. In IC engine also you have seen that after combustion we are getting highest temperature. Okay, so 3 to 4 is your turbine. So 1 to 2 we are assuming isentropic. If it is not isentropic, then 2s you can put, 4s you can put. Okay, so this is your simple gas turbine system. So it is having then one isobaric process or constant pressure process, two constant pressure process, that means 2 to 3 and 1 to 4 both are constant pressure process, and two isentropic process 1 to 2 and 3 to 4 isentropic. Okay, ideal cycle will have two isentropic, two isobaric process. Fine. Okay, next one. Okay, so next one, let's see the difference between the cycles, among the cycles: Carnot cycle, Otto cycle, Rankine cycle, diesel cycle, Ericsson cycle. So many cycles we discuss actually. So Carnot cycle, if I draw in PV diagram, PV, so it will be like this: 1 2 3 4. Okay, so Q coming, Q going. Okay, so this is your Carnot cycle process. Now if I go for Otto cycle, Otto cycle PV diagram, PV, so we have drawn like this. You can remember IC engine discussion, reciprocating IC engine, 1 2 3 4. This is Otto. Then another cycle I did not discuss actually, this is Ericsson cycle, PV. Okay, so their numbering a little bit different, but does not matter. 3 4. This is Ericsson. The next is diesel cycle. You can remember diesel cycle, then your Brayton cycle. So this whatever gas turbine system I am discussing, this is based on Brayton cycle. So PV diagram will be like 2 to 3. So 1 2 3 4. Okay, you can see the differences. So if I draw these like basic cycles, like say Ericsson you ignore, and other cycles in common cycle, Okay, 1 2 3 4. Okay, so all the cycle actually I want to draw in one cycle. TS. So 2 to 3 is, let's say, first you draw Brayton cycle. So 1 to 2 constant pressure process. Wait, wait. PV or TS? I'll draw PV. Okay, so PV diagram, let's see. So 1 to 2 is constant pressure process. Okay, so heat air intake happening. Then 2 to 3 you're compressing. So 3 to 4 your combustion happening in Otto cycle. You can see, remember, you can see the Otto cycle. 2 to 3 is vertical, here 3 to 4. Okay, uh, and 4 to 1, wait, okay, so 1 to 2 constant pressure process, 2 to 3 adiabatic process, 3 to 4 constant volume process, 4 to 1 again adiabatic process. Now if I want to draw Otto cycle from this one, Otto cycle means I will have 2 to 3 process, 3 to 4 process, 4 to I'll have, okay, so Otto cycle here 2 3 4 5, correct? Everyone okay? Okay, so 2 3 4 5 is Otto cycle. Now if I want to make this one as a diesel cycle, so what will I make? 2 3 4 5 6 maybe, 2 3 6 5 2. I should make like this. So diesel cycle. So if I want to make this one as your Brayton cycle, so Brayton cycle like 1 2 3, 1 to 2 intake, 2 to 3 compression, compression by constant heat addition, constant pressure. So 3 to 6, 6 to 1 again expansion process. Okay, so this is Brayton cycle. So in single cycle actually I can draw like this. Okay, in exam also I can give one single cycle, I can ask you to identify which one what cycle. Okay, now we'll discuss details about Brayton cycle. So again, you should not forget this figure: compressor, combustion chamber, turbine expansion, 1 2 3 4. Okay, and instead of making open cycle, you can make close also for temporary purpose. So W turbine, compressor, W turbine, heat coming Q1, and heat rejection is happening, you can assume here. Okay, so net work output W turbine minus W compressor. Okay, now you draw PV diagram. PV, constant pressure process, 2 constant pressure process, 4 1 2 3. Okay, now TS diagram. TS, so 2 constant pressure line, 1 4 to 1, 1 to 2 compression process, 2 3 4 4 to 1. Okay, so this is your TS and PV diagram. Now if I want to compare with Rankine cycle, so how it will look like? TS diagram, three 1 2 3 4, then A B C D. Okay, this is Rankine, this is Brayton. Okay, Brayton is upper side at high temperature because there condensation is not happening. Okay, so that's why Brayton is on the upper side. And pressure range, you can see P1, P2. Within these two pressure range, both are working fine. So similar way, PV diagram, if I draw, so 3 to 4 is compression happening, volume reducing. 4 to 1, constant pressure process. 1 to 2, again expansion happening. So 3, 4, 1, and A to B compression happening, A to B, and D, C. Okay, this is your Rankine cycle, this is Brayton cycle. Okay, you can see the difference between Rankine cycle and Brayton cycle from these figures. Okay, so Brayton cycle will be working at higher temperature, so there will be no condensation, so there will be no two-phase thing. Okay, but Rankine cycle will have two-phase thing. That's why this vapor envelope will be coming, and mixture is story will be coming in between. So yeah, so Rankine cycle diagram will be like this. The boiler is there, then turbine, then condenser, then pump. Okay, so if I put the numbers 3 to 4, 3 to 4 is pump, 3, 4 pump, 2 to 3 condenser, after boiler it is 1. Okay, this is Rankine, this is Brayton. So 1 to 2 expansion process. Okay, whenever you're drawing figure, you should give proper arrow symbol, otherwise I may cut marks, because if you do not understand flow direction, then actually there is meaningless of drawing Rankine cycle or Brayton cycle or any type of cycles. Okay, now we have to calculate the thermal efficiency of Brayton cycle. So first you draw TS diagram, two pressure line, constant pressure line first you have to draw, then 1 to 2, 2 to 1, 2, 3, 4. Okay, so as whatever you follow your number notation, based on that you have to derive your formula. Okay, so eta thermal efficiency equals W net power output and heat input. Okay, so heat input Q1 and power output WT, this is W compressor. So W net net means WC minus WT minus WC divided by Q1. Q1 is a heat input. Okay, so now if I write like this, Cp T3 minus T3 minus T4 minus T2 minus T1 divided by Q1. Q1 is Cp again, T3 minus T2. We are assuming Cp constant. Okay, constant specific heats. So Cp constant we are assuming. So T2 by T1 equals P2 by P1 K minus 1 or gamma minus 1 by gamma. T3 by T4 equals P3 by P4 gamma minus 1 by gamma. P3 equals P2, you can see the same constant pressure line, and P4 equals P1. So T2 by T1 equals T3 by T4 or T4 by T1 equals T3 by T2. Okay, so then I can put all the values here. 1 minus T4 minus T2 T3 minus T2 equals 1 minus T1 by T2 T4 by T1 minus 1 T3 by T2 minus 1. Okay, So this is giving me 1 minus T1 by T2. Now 1 to 2, process 1 to 2, what is happening? T2 by T1 equals P2 by P1 gamma minus 1 by gamma equals RP, pressure ratio, gamma minus 1 by gamma. Okay, eta thermal efficiency equals 1 minus 1 by RP gamma minus 1 by gamma. Okay, so this formula you should remember for Brayton cycle thermal efficiency, R pressure ratio for gamma minus 1 by gamma. Now if I have compression ratio known, let's say RK is compression ratio. Okay, so in that case T1 by T2 equals P1 by P2 gamma minus 1 by gamma equals V2 by V1 specific volume K minus 1 or gamma minus 1, gamma minus 1. So eta equals 1 by RK gamma minus 1. Okay, RK means compression ratio. So you have to see whether pressure ratio given or compression ratio given. So both may not be same. Okay, if compression ratio given, formula is different, pressure ratio given, formula is different. Okay, so comparison between OTTO and Brayton cycle, again you have to draw PV diagram. Already we have given a general diagram, so based on that only. Okay, 1 2 5 3 4 6. Okay, so 1 2 1 2 5 6 Brayton, 1 2 5 6 6 1 Brayton, 1 3 2 3 4 OTTO cycle. Okay, okay, so I'll draw this one in TS diagram. Okay, so two pressure line and it is like this, 1 to 2, okay, constant pressure, and 2 to 5, 2 to 5 is constant pressure process. So this is P equals C, V equals C, then okay, so 2 to 3 is your 2 to 3 is your volume constant, and 2 to 5 is your pressure constant, and 1 to 4 is volume constant, and 1 to 6 you can see your pressure constant. Okay, so this way you can draw your figures. So you can just comparative figure you can draw in TS diagram. So Brayton cycle for reciprocating engine is not suitable because this engine cannot handle such large volume flow. Okay, but Otto cycle or diesel cycle, it will be handling very smaller amount of volume flow. Okay, next, spelling mistake. So effect, regeneration and Brayton cycle. So effect of regeneration. So first you have to understand what is regeneration. Regeneration means you are using certain amount of heat to increase your performance. System performance will be increasing. So okay, let's assume like this. Then heat gen addition is here, it is here, it is going here. Okay, so compressor, turbine, shaft. Okay, so from compressor your compressed air is going through this heat exchanger. Okay, this one heat exchanger. And then your combustor, from combustor you are fluid is going to turbine, and turbine, after that you have seen already in gas turbine engine of General Electric that about 500 degree temperature is there. So very high amount of heat is there already. So that heat you are using in heat exchanger. What you are doing after compression, actually you are increasing air temperature. Okay, so some energy you are extracting from your exhaust heat and increasing that compressed air temperature. So that will be reduce your combustor heat input. Okay, so this is called regeneration. Okay, so instead of wasting certain amount of heat, you are regenerating or you are reusing to increase your compressed air temperature. Okay, so you are using for compressed air temperature. Okay, so then what will be my TS diagram then? Again, you draw your pressure line, 1 to 2 numbering. You have to give a number where here it is 1. So they have drawn like complete closed cycle. Okay, so you can create open cycle also, doesn't matter. 1 to 2 your compressor. Okay, isentropic compression we are assuming. Then 2 to 3 4 3 is here, 3 to 4 is here, 4 to 5 they are giving here. Okay, fine. And then 6. Okay, so we'll see. 1 to 2 is happening like compression happening, then 2 to 3 is your heat addition process, 3 to 4 your turbine work. Okay, so for 4 to 1 heat should be rejected at constant pressure. So what they are doing, 4 to 5 the process is there. Okay, so 4 to 5 means you are giving heat to at constant temperature. Just wait. 2 to 6. Okay, so 4 to 5. Just wait. What is happening here? 2 to 6. 2 to 6. Something wrong happened. What happened here? Heat exchanger. 5 is wrong place, right? Location is wrong. This is 5 you are saying. Maybe 3 dash we can make. So 4 to 5. No, 4 and 5 pressure is same, no? Four to 5 pressure is same. Why pressure will be changing? Right? 4 to 5 pressure is not changing. Then 5. Okay, 5. Then another heat release is happening. They are saying 5 to 1. What is happening? But pressure you are not changing, no? Heat exchange is 2 to 3. Now something wrong. Maybe I'll check. Okay, so I'll hold it. So next day maybe I'll record this part. This slide. Or if I get back later. So this one I have to recheck. So we'll see effect of irreversibility. Every time I was saying like ideal cycle and actual cycle, so there will be irreversibility term. So TS, again you draw your cycle 1 2, here they have given 0 3, so as it is from some book I am copying 5 4 5, so 0 to 3s, 4 to 4, this is 5s, 3, this is 5s, means they are saying constant entropy, this is 5, this is PO, this is P3, and T4 equals maximum temperature. Okay, so del H for turbine, work of turbine, and eta turbine. So W actual by W ideal. Okay, so eta compressor equals W ideal, this for turbine. Okay, W actual. So you can see the formula is opposite just way, because compressor will be taking more energy, turbine will be giving less energy. That's why this is opposite. So eta turbine formula becomes H4 minus H5 divided by H4 minus H5s. H4 H5 H4 H5s. Okay. Now for compressor, this formula will be like this: H3s minus HO, H3 minus HO. Okay. Now eta thermal, net work by Q1 equals 1 minus T5 minus TO, TO minus T3. Okay, this is your network thermal efficiency.